Hello students, last time we have started the chapter chemical equilibrium. Today we will continue that chapter. Today we will discuss about the equilibrium constant with respect to partial pressure, that is Kp. The equilibrium constant, you know that the equilibrium constant is denoted by symbol capital K. It describes the extent to which reaction proceeds, that is the position of chemical equilibrium. You consider this reaction, general reaction, reversible general reaction, as AA plus BB gives CC plus DD. Now for this reaction, you can write the expression for Kc as Kc is equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. And for the same reaction, if it is in a gaseous state, you can write the expression of equilibrium constant as Kp in terms of pressure as Kp is equal to Pc raised to C into Pd raised to D divided by Pa raised to A into Pb raised to B. Okay. Now let this A, B, C and D be gases in the following gaseous reaction. Then you can write the expression for Kp like this. Now what are these Pa, Pb, Pc and Pd? They are the partial pressures of the gases A, B, C and D respectively in the mixture at equilibrium. Now we'll derive the relation between Kp and Kc. You know that Kp is equal to concentration of Pc raised to C into concentration of Pd raised to D divided by concentration of Pa raised to A into concentration of Pb raised to B. Now this is for the general reaction AA plus BB gives CC plus DD. Now we know that partial pressure P is equal to nRT upon V. That is, you can obtain this expression from general gas equation. Now the partial pressure of A, you can write as Pa is equal to nART upon V. Suppose volume is 1 liter. This volume is 1 liter. Then you can write Pa is equal to concentration of ART. Similarly for B, C and D, we have this expression Kp is equal to Pc raised to C into P raised to D, Pd raised to D divided by Pa raised to A into Pb raised to B. So by substituting the values of Pa, Pb, Pc and Pd, we can finally write as Kp is equal to concentration of CCRT raised to C, CDRT raised to D divided by CART raised to A into concentration of CBRT raised to B. By rearranging, you can write as Kp is equal to Cc raised to C into Cd raised to D divided by Ca raised to A into Cb raised to B into in bracket RT raised to C plus D minus A plus B. Again, you can write as Kp is equal to Kc. What is this term? This ratio is nothing but Kc. So we can write as Kp is equal to Kc in bracket RT raised to delta Ng. What is this delta Ng? It is nothing but number of gaseous moles of products minus number of gaseous moles of reactants. Is it clear? So this is the relation between Kc and Kp. The question may be asked, derive the relation between Kc and Kp. Now we'll discuss about the homogeneous and heterogeneous equilibrium. Homogeneous and heterogeneous equilibrium. Now in homogeneous equilibrium state of all reactants and products are in the same phase. In homogeneous equilibrium state of all reactants and products are in same phase. We consider this reaction, reversible reaction, as twice HI gaseous gives H2 gaseous plus I2 gaseous. So this is the homogeneous equilibrium for this reaction. You can observe here that all the substances are in gaseous state. It is known as homogeneous equilibrium. Next is the heterogeneous equilibrium. Now this heterogeneous equilibrium results from a reversible reaction involving reactants and products. Those are in different phases. Can consider this reaction as ammonia gaseous combines with chlorine gas. The reactants are in gaseous state, but they combine to form the product ammonium chloride solid. There are different phases. So it is the heterogeneous equilibrium. Now we'll discuss about the equilibrium constant for homogeneous or heterogeneous equilibrium. First we will discuss about the equilibrium constant for heterogeneous equilibrium. Consider this reaction. C2H5OH liquid gives C2H5OH gaseous. So this is the heterogeneous equilibrium. For this heterogeneous equilibrium, you can write the expression for Kc as Kc is equal to concentration of C2H5OH gaseous divided by concentration of C2H5OH liquid. But the concentration of C2H5OH liquid is equal to 1. So what is remaining? You can write simply as Kc is equal to concentration of C2H5OH gaseous. So this is the equilibrium constant for this heterogeneous equilibrium. Now we will discuss about the units of equilibrium constants. What are the units of equilibrium constants? The unit of equilibrium constants depends upon the expression of Kc. It depends upon the expression for Kc. Which is different. The unit of equilibrium constant depends upon the expression of Kc, which is different for different equilibria. So the unit of Kc is also different. We'll consider these two reactions, equilibrium reaction number 1 and equilibrium reaction number 2. You consider the first reaction, H2 gaseous plus I2 gaseous gives twice HI gaseous. For this reaction, you can write the expression for Kc as concentration of HI gaseous raised to 2 divided by concentration of H2 gaseous into concentration of I2 gaseous. Now the unit for Kc you can write as in bracket mole per dm cube raised to 2 divided by mole per dm cube into mole per dm cube. So here also you can write as mole per dm cube raised to 2. So both will be cancelled. What is remaining? All the units are cancelled out. Therefore, Kc has no unit for this reaction. Okay. You consider this another reaction. N2 gaseous plus thrice H2 gaseous gives twice ammonia gas. Now, you can write the expression for Kc as concentration of ammonia gaseous raised to 2 divided by concentration of nitrogen gas into concentration of hydrogen gas raised to 3. Now we'll see the unit of Kc for this reaction. You can write as Kc equal to concentration of mole per dm cube raised to 2 divided by, in bracket, mole cubic decimeter into, in bracket, mole per dm cube raised to 3. So again you can write as Kc equal to, in bracket, mole cubic decimeter raised to 2 divided by, here 3 plus 1 is 4. So divided by mole per dm cube raised to 4. So what is remaining? If you take this for here in the numerator, it will be minus. So 2 minus 4, that is minus 2. So we will get Kc equal to, in bracket, mole per dm cube raised to minus 2. If you solve this bracket, you can write as Kc equal to mole raised to minus 2 into dm raised to 6. So these are the units for equilibrium constant. So you can observe that the unit of equilibrium constants depend upon the expression of Kc, which is different for different equilibria. So the unit of Kc is also different. Is it clear? Okay. Now one more hint is here for the unit of Kc. The simplest way to calculate units of Kc is a difference between number of moles of the numerator and number of moles at the denominator in equilibrium constant expression. Now with respect to expression second, just we have seen in the last slide, the difference between number of moles, that is delta n equal to 2 minus, in bracket, 1 plus 3, that is equal to 2 minus 4, and that is equal to minus 2. Therefore, unit for Kc will be equal to, in bracket, mole per dm raised to delta n. And what is delta n? It is nothing but minus 2. So unit for Kc will be equal to, in bracket, mole per dm cube raised to minus 2. That is mole raised to minus 2 dm raised to 6. Similarly, with respect to expression 1 in the last slide, you can write the unit of Kc as, it is equal to, in bracket, mole dm raised to minus 3 raised to delta n. What is delta n for that reaction? Delta n is 0. So in bracket, mole dm raised to minus 3 bracket raised to 0. So what is it? It is nothing but 0. Therefore Kc has no unit. So this is the shortcut for expressing the unit of Kc. Is it clear? Now we'll discuss about the characteristics of equilibrium constant. The first point is given as the value of equilibrium constant is independent of initial concentration of either the reactants or products. Is it clear? What is given? the value of equilibrium constant is independent of what? Initial concentration of either the reactants or products. Second point is given as the equilibrium constant is a temperature dependent. Hence, Kc, Kp change with change in temperature. Is it clear? The third point is given as equilibrium constant has a characteristic value for a particular reversible reaction represented by a balanced equation at a given temperature. And the last point is given as higher value of Kc or Kp means what it means? It means more concentration of a product is formed and the equilibrium point is more towards right hand side and vice versa. Is it clear? So these are the characteristics of equilibrium constant. Okay, thank you.